All right, now we're gonna go over the right answers to the homework that you should have done yesterday. All right, and there were, let's see, how many questions? 7, 8, 9 questions that you needed to do. And there was a group of 7, and then there were some practice problems 1 and 2 that you needed to do that you should have already submitted. So first question said, state the difference between a physical and a chemical change and list 3 likely indications that a chemical change has occurred. Right? Physical, same stuff. We didn't change the properties. It's all the same stuff. We keep talking about the idea of Kool-Aid. Everything that's in there keeps its original property. Water keeps it liquid. Sugar makes it sweet. Food coloring gives it a color, and the flavoring makes it taste like cherry. All right, that's a physical change. Chemical change, new stuff. The rust that's on my truck. Right? It's not iron anymore. Now it's iron oxide. It bonded with the oxygen. The only way I'm getting that apart is got to take my truck in and scrap it, ultimately. Hopefully that doesn't happen for many years. I hope. I want to keep my truck for a while. Right? How do we know if that chemical change has occurred? Well, if there's a gas that's given off, if we see it bubble, that means there was a chemical change took place. If there's a change in color, if I see a change in color, like the idea of rust all of a sudden looks different, because I see a change in color, that indicates a chemical change. If there's energy given off, like boom, something blows up, that's some energy being given off. That is a chemical change that took place. Or if a precipitate is formed, I take 2 clear liquids, pour them together, all of a sudden it turns really cloudy, and that cloud doesn't dissolve. Right? That means a chemical change took place. Those were the 4 things. Question number 2. Classify each as a physical or chemical change. Letter A, cookies are baked. One way to look at these is, can I get my original stuff back? Okay, so making cookies, I put water, I put flour, I put sugar, I put baking soda in, I mixed it all up, and I put it in the oven, I baked it. Now, can I get my water back, my flour, my sugar, my baking soda? Can I get all that back from the cookie after it's baked? No, I can't. It's already been all chemically combined together, makes this delicious little cookie to eat. That is a chemical change because it changed it. Letter B, water boils. I boil some water, it turns into water vapor. Excuse me, can I get that water vapor to turn back into water? Yep, all I gotta do is cool it back down. Drip, turns back into water. All right, so that's a physical change. If letter C, salt dissolves in water. Can I get that salt out of the water? Allow the water to evaporate. Heat it up, make it boil, make it speed up the evaporation. Right? And then I end up with a container that's just got the salt. Yep, I can get it back. It's an easy process to get it out of there. That's a physical change. Letter D, a firefly emits light. Well, that's actually a chemical process on that one. He's actually doing a little chemical change inside of his body to make it so that he lights up at night. I don't know if you guys know that you can determine the temperature at night based on the speed at which fireflies light up. The faster they blink, the warmer it is. The slower they blink, the cooler the night is. Okay? So that heat actually influences how fast that chemical reaction takes place inside of them. Letter E, milk spoils. Well, after milk goes bad, can you get the original good milk back? No, it's gone. So that's a chemical change. And the last one, this one, letter F, a metal chair rusts. Once it rusts, can I get the iron back easily? No, it's going to be a hard process. I got to heat it up really high. That's a chemical change. Right? All right, number 3, state several physical or chemical properties that could be used to distinguish between each of the following pairs of substances and mixtures. So how can I tell the differences on them? Well, first one, you got some gasoline, you got some water, you got 2 containers. How do you tell the difference? Well, one would be, can you smell it? That would be one way. You could smell the gasoline. The water wouldn't have any smell. You could also look at color. Gasoline has kind of a yellowish color. Water hopefully doesn't have a yellow color to it. It should be clear if it's just straight up water. So that would be a couple ways. You could also measure its density. Gasoline has a certain density. Water has a density. Gasoline has actually a lower density than water. That's why it floats on top of the water. It has a lower density and the water sinks. Letter B, copper and silver. Well, how do we tell the difference in that? We can look at the color. A copper ring versus a silver ring, they look different. We can use density. They have different densities. We can use that. That's how they separate them when they recycle the 2 things. Letter C, water and salt water. So I have a cup that's got some water and a cup that's got some salt water. How do I tell the difference? Well, I could taste it. That would be a way to check. I could use the density, and I could measure the density of them, because once I add that salt to the water, it changes the density. That's why in the Dead Sea over on the other side of the world, people like to go swimming in it because it's got lots and lots of salt in it. And we actually, when you sit in it, when you go in it, you actually float really high in the water. because you are way less dense than salt water. And people say that it's a really neat experience to float inside the Dead Sea because it's got a lot more salt than the ocean does. The last one, letter D, aluminum versus steel. Well, you look at the color, there's a little different color between aluminum and steel. Steel is kind of silvery, and aluminum is kind of a really, I want to say, almost like a really, well, let me back up. Steel is a dark silver. Aluminum is kind of like a light silver color. So there's a different density. Another one that's really common when I recycle things is I have a magnet in my truck. And if I put a magnet to it and it goes into it and it's attracted, then it's steel. If it doesn't attract to it, sit there and like put it on there and doesn't do anything, then that's aluminum. And you actually get more money for aluminum than you do steel. So I actually separate the things out and sell them separately at the scrapyard and get a few dollars for some stuff that normally I would just throw away. So might as well get paid for it instead of just giving it away. It's something that you can do on the side if you want. Just pick up scrap stuff and you can take it to the scrap yards here in town. There's a couple of them that will take the stuff. So number 4, hydrogen and oxygen react chemically to form water. We take hydrogen, oxygen, put them together, it makes water. Okay? How much water could be formed if all 4.8 grams of hydrogen reacted with all 3.8 grams of oxygen to make water? Well, in this one, actually, all you're going to do is you're just going to take that 4.8 the hydrogen, you're going to add that to the 38.4. You add those two together, they go together, and that's going to tell us how much water we should make. And if you add these together, you get 43.2 grams of water that would be made. Okay, because all of this and all that's going to go together and make all that on the other side. Well, then I have a challenge question there, one to really make you think. Law of conservation of mass states that matter cannot be created nor destroyed. According to this law, how many grams of water are formed if the following reaction occurs? So we're going to get 14 grams of nitrogen, 8 grams of oxygen are formed from 40 grams of ammonium nitrate when it explodes. That was actually over in, Beirut, where they had the big explosion that leveled the town a few months ago over the summer. The ammonium nitrate, that was the substance that did that. They had a whole bunch of tons of that stuff that was unstable and it blew up. When it breaks down explosively, it forms nitrogen gas, oxygen gas, and water. So what we end up with this one is we're going to get the ammonium nitrate, there's 40 grams of it. Well, that's actually made up of 14 grams of nitrogen plus 8 grams of oxygen plus some amount of grams of water. Okay, so what we got to do is we got to make this one X. So if we add these things together, these two are 22 plus X equals 40. So how do I find out what that X is? Well, subtract 22 from both sides. That makes X equal 18 grams. So we know now there is 18 grams of water that was made. Right? It's all because everything that's on this side has got to equal how much is on that side. All right. Number 6, how does agitation increase the amount of solute that dissolves in a solvent? Well, we make more contact between the solute and solvent. When I stir it up, then it makes it come in contact and we can fill in those little holes that were in the drawing that we had in our notes when I was showing you the water. Number 7, what does an increase in temperature do to the solubility of the following? So letter A, if I have carbon dioxide in a bottle of pop, I'm raising the temperature. What does that do to gases? It lowers solubility. So it's going to go down. All right. Letter B, salt and water. Raise the temperature of the water. Salt is a solid, so it actually raises the solubility. I can put more salt in the water. Letter C, oxygen in lake water. If I raise the temperature of the lake water, then the oxygen level is going to go down, and ultimately I could end up with a whole bunch of dead fish that are going to suffocate because there isn't going to be enough oxygen in the water for them. Okay. All right, then we go to the very last one, the practice problems that involve that equation, which was S1 over P1 equals S2 over P2. All right, that was the equation we're going to use. So the first one, we got a solubility of gas and water. So the solubility of gas and water is 0.16 grams per liter. So if I use my little chart that I had, I got 1, 2 systems, and I got S and P. Oops, another line there. Okay, so I've got 0.16 grams per liter. That's my solubility to start with. And that's at a thing called 104 kPa. Well, that's another unit of pressure, kilopascals, that we'll learn more about later. What's the solubility when the pressure of the gas increases to 288 kilopascals. So we're going to go up to 208 kilopascals. We want to know what's the solubility at that level. Okay. So now I'm just going to put this stuff in. Here's S1, here's P1, here's S2, here's P2. All right. So we put this in, we get 0.16 over 104 equals X over 208. All right, now I got to cross multiply. So I'm going to take this one times that, the top one times the bottom. So I get 104 times X equals 0.16 times 208. Now I got to get X by itself, divide both sides by 104. And you do that, and X ends up equaling 0.44 grams per liter. Now, what does this mean? Well, originally we had a solubility of 0.1. Oh, there goes the lights again. Hold on. So what does that mean? Well, originally we had a solubility of 0.16. Here's our starting solubility. The solubility changed to 0.44. Did I get more stuff into this? Yep, sure did. I got a higher solubility. I put more gas into this liquid. All right. Okay, so that was the first one. Now let's go to the next one, number 2. So get rid of this. We're still going to use the same equation. All right, this time it tells us we've got a solubility, or we got water that's 0 degrees Celsius at a pressure, and it's got 3.6 grams per liter. So 3.6 grams per liter at a pressure of 1 atm. And it says what pressure is needed to produce an aqueous solution containing 9.5 grams per liter. So I need 9.5 grams per liter. We want to find out what's that new pressure I need. Temperature didn't change. If you notice, it went from 0 degrees Celsius, 0 degrees Celsius. So we can ignore that temperature piece because it stays the same all the way across. So again, here's S1, here's P1, here's S2, here's P2. So we're going to have 3.6 over 1 equals 9.5 over X. Cross multiply, go this times this and this times that. So we get 3.6 times X equals 9.5 times 1. Then divide both sides by 3.6. And X is going to end up equaling, the answer is 2.6 grams per liter is the answer. So now again, we started the, oops, sorry, 9 grams per liter. Look at that, I made a mistake already. Y'all should have caught that. That was pressure, so it's ATMs. So the pressure was 1 ATM. It changed over to 2.6. What happened to the pressure? The pressure went up. So in order to get this 9.5, we got to raise that pressure up to 2.6 ATMs. All right, well, that gets us the answers to all those. So we'll see you coming soon. Have a great day.